All right, welcome everyone again. So in this video, we are going to introduce the idea of cumulative distribution functions, which we will very often just abbreviate to CDFs. And so our goals here are we want to be able to define what a cumulative distribution function is. We want to be able to derive one for just a very small example. And we just want to state a few properties about these cumulative distribution functions. And so we'll start with the definition. And so the definition is given here. I'm on the last couple of pages of this note packet, by the way, so we've skipped over a couple of pages in the meantime. And so this function is defined just as the probability that a random variable y is less than or equal to some specific value little y. Likely, this quantity should look at least a little familiar because we've made these types of calculations before. These are calculated with the p functions in R. And so we've never calculated a full CDF before, but we've calculated pieces of them because we've made this type of calculation with some common discrete distribution functions. And so, for example, we could think about this binomial example with n equal to 3 and p equal to 0.5. We can obtain the PDF, which is given as part of the problem. And if we were, for example, to do something like p binom 1, 3.5, that will give us the probability that y is less than or equal to 1, which in this case is 0.5. Something that I'd like you to note is that unlike the PDF, the CDF is defined for any value of y. So y can be between negative infinity and positive infinity. And so, for example, you will not get an error if you put in to p binom, say, 2.6. That is the probability that y is less than or equal to 2.6, and that has a value of 0.875. So y can be 0, 1, or 2. Similarly, you will not get an error if you put in something like negative 40. The probability that y is less than or equal to negative 40 for this example is 0. Y can't be less than or equal to negative 40. So you'll still get a value for the CDF. You won't get an error. You'll just get a 0 in this case. We'll do one more. So you could also throw in, 102. So you could do a quick quiz for yourself. What's the probability that y is less than or equal to 102? That is 1. So again, you'll get an actual value for this cumulative distribution function. Okay, so we have the PDF for y for this example. So let's derive the full cumulative distribution function and plot it. And so this is going to be the greatest test of my iPad skills, which are very lacking, but I'm going to do my best here to make a somewhat neat plot. And so on the x-axis of our plot, we're going to put the possible values of y. On the y-axis, we're going to plot the CDF, which is the probability that the random variable y is less than or equal to a particular value of y. And I'm going to start my plot on the x-axis at negative 1 and go up to 4. And then I'm going to start my y-axis at 0, and I think I will do increments of 0.25. Okay, so for this simple example, what is our CDF going to look like? So one way you could think about this is you could think about how much probability is accruing as you move along the x-axis. And so the probability that y is less than or equal to -1 is 0. The probability that y is less than or equal to -0.5 is 0. And you keep going all the way until you get to 0. Once you make it to 0, then what's going to happen is there's going to be a jump because the probability that y is less than or equal to 0 is 0.125. And so it's going to jump up to 0.125 on that y-axis. And then you could keep going. So probability that y is less than or equal to a fourth is still 0.125, and you can follow that logic through until you get to y equals 1. Once you make it to y equals 1, the probability that y is less than or equal to 1 jumps again. And so this time it jumps up to 0.5. So it jumps up to 0.5 because it's the 0.125 plus the 0.375 is the probability that y is less than or equal to 1. And then you keep going. So I'm not going to go as slowly now, but once you get to 2, the jump up is by another 0.375, and so you wind up with, I believe, 0.875, and then you get another jump when y is equal to 3. That jumps you up to 1. Anything past 3, the CDF is going to be valued at 1, because the probability that y is less than or equal to, say, 5.5 is 1. And so you remain at 1 for the rest of the graph. Similarly, down in the lower left, you remain at a probability of 0 for any value of y that's less than 0. So that's our plot of the CDF. We are also going to write out what this looks like as a function. And so our capital F of y, we're pretty much going to obtain from the plot. And so the CDF is going to be equal to 0 when y is less than 0. It's going to be equal to 0.125 when y is between 0 and 1. It's going to be equal to 0.5 when y is between 1 and 2. 0.875 when y is between 2 and 3. And it's going to be equal to 1 if y is greater than... not 1, if y is greater than 3. All of that is derived from the plot. One thing to notice or maybe be careful of are these inequality signs, which do matter. And so once y reaches 0, it immediately makes the jump in probability. And so that's why this is a less than or equals to sign. And then once y reaches 1, it again makes that jump up. And so that's why on the left part of the inequalities, we have a less than or equal to sign, but on the right, we have a less than sign. Okay, so that's our CDF, both graphically and in function form. For a discrete random variable, notice that, and this is true for all discrete random variables, the CDF is a step function. And so it's a step function, meaning that you kind of get this flat shape with different steps. And the steps occur where there is some positive probability. So the steps occur where the probability that the random variable y is equal to some value little y is greater than 0. And so we've seen that in the graph that we have constructed. The final part of this video will talk about a few properties of these cumulative distribution functions, all of which we could see from the graph. And so the first two are a couple of limits. So as y goes to infinity, eventually this property says that we will reach a point where the CDF is 1. So in our graph, that happened pretty quickly, but the property says that eventually for any distribution, you'll get the CDF equal to 1. And as y goes to negative infinity, eventually the CDF will become 0. So eventually you reach a point where no probability has accumulated. The third property says that if you have two values, y1 and y2, and y1 is less than or equal to y2, then the CDF evaluated at y1 must be less than or equal to the CDF evaluated at y2. Again, we could see that in the graph, and what this property really says is that CDFs are non-decreasing functions. So they're not necessarily increasing because they're allowed to stay the same as y goes up, but they're never decreasing. There's a last little property here that we will end up applying in class, but at this point you should have enough information to jump over to the prep quiz to answer some questions.